very much. Thank you very much for having me today. Um, as I mentioned just a few moments ago, I wish I could be in Korea at the moment, and thank you very much for inviting me next time. So please keep the invitation up. Uh, for anything I mention in this talk that is unclear, or you want to follow up, or maybe there's a project that will spur from what I'll discuss today, please contact me. That's my email. And if you are in California, as some in the audience, I'm looking at you, Matt. No, UC Santa Cruz is a beautiful campus. My office is right around here somewhere. So there's a view of the bay that is truly stunning. So please reach out if you're ever on the West Coast, on the other side of the pond from where you guys are. I will talk about lots of things today. And I am sure I will not have time to go in as much depth as I or you would like about all of the topics that I'll be talking about. So please do feel free to ask me either during the talk or after the talk, and I'll be very happy to follow up with anything you're curious about. So we live in an era where we really have a standard model of the universe at large, but also the universe when it comes down to local structure. For instance, we know conclusively that our own Milky Way is encompassed by a large halo of a non-relativistic substance that we call dark matter, for lack of a better name. And there is also very convincing evidence that on a global, universal scale, this substance, this dark matter, actually accounts for the majority of the matter budget in the universe. We know now that that's about 80% or so of the total matter budget of the universe. Also, there is conclusive evidence that I unfortunately will not have time to review today, that this dark matter does not belong to the standard model. It is, in fact, a new fundamental constituent. So what we'd like to think of as a new elementary particle. Now, this is therefore a good point to stop and ask the question, what is an elementary particle? And so I'm a particle physicist, and suppose that a particle physicist goes on a date. I've been married for 20 years, so I don't know how that feels. But suppose you're on a date and you're a particle physicist, and your date asks you, well, what do you work on? And you say elementary particles. Well, what is an elementary particle? And there's one way in which your date is guaranteed to become a complete disaster. And that way is, as often is the case, is to say the truth, to tell the truth. And the truth is that an elementary particle is an irreducible unitary representation of the Poincare group. Now that's a mouthful, and that's a scary thing to say, especially on a date. But there's actually quite a bit of physics in this technical definition. In fact, due to a theorem by these cheerful Hungarian-American mathematician and physicist Eugene Wigner, we know that all such representations are cataloged by two numbers. One number that qualifies, transformations that include rotations and Lorentz transformations, that's a mass. And a second number that is either integer or half integer that qualifies how this elementary particle transforms under rotations. So since we are dealing with a new constituent, it makes sense to ask the question, well, what do we know about the mass and the spin, which is the technical name for the integer or half integer number I was alluding to, of the dark matter? Well, the first thing that we know of is that the dark matter clusters gravitationally on scales at least as large as the scales of dwarf galaxies. Now, dwarf galaxies are small galaxies, Many of them are satellite galaxies. This is an example of a satellite galaxies. And for gravitational collapse and for the gravitational stability of these objects, uh, we need to have an elementary constituent whose quantum wavelength does not interfere with gravity. In other words, we need the de Broglie wavelength of the object that we identify as the dominant component of dark matter to be smaller than the size of the smallest collapsed structures we observe in the universe. And that's, roughly speaking, a kiloparsec. In more human or non-astronomical units, that is 3 times 10 to the 21 centimeters. And since we know the velocity dispersion of these objects, we can actually write the de Broglie wavelength in terms of the mass of the constituent. And this is what you get. So for 1 electron volt of mass, the de Broglie wavelength of an object in a dwarf galaxy is about that much, 0.3 centimeters. Therefore, the dark matter must be more massive than 10 to the negative 22 electron volts. This is more or less a fairly solid lower limit to what the dark matter mass can be. Please notice that if the dark matter is so light, you certainly need a bosonic field. And the reason is that you need to stack many, many, many of these dark matter particles in order to obtain the mass of the observed galaxy. But of course, you're limited by the fact that the momentum of the particle at that mass is on the same order of magnitude as the size of the object. And so you don't have any free phase space, and therefore you have to have bosonic particles. For fermions, the limits are much better. They're about, in fact, 10 to the 25 times better. We're talking about a few keV if you apply the same line of reasoning to fermions. Now, what happens if the dark matter as a point object is very, very heavy? Well, if the dark matter is heavy and you imagine a dark matter particle passing through a system like this is a globular cluster, or a system like this, a disk galaxy, you can easily imagine that these systems would get warped, disrupted, deformed, as opposed to what they are observed to be, which is very, very stable over billions of years. And so turning this argument into a quantitative statement, you can convince yourself that the tidal disruption of structures implies that the dark matter as a point object must be lighter than 10 to the 67 electron volts. That's in solar mass units about a few tens of solar masses. And if you're curious about the state of the art of these type of arguments, with my collaborators last year, we actually produced the most updated and fully numerical limits that pertain to this type of argument. So please ask me if you're curious. So going back to the mass and spin of the dark matter, we have a staggering landscape that I'm sure many of you are familiar with, that is wider than 90 orders of magnitude, confined on the one hand by quantum mechanics, on the other hand by macroscopic gravitational tidal effects. Within this large landscape, we, and I say we in the sense of the collective ensemble of people thinking about what the dark matter is, we've had a love affair with one particular segment of this landscape around the electroweak scale. And we've invested a lot of time. We've written many, many hundreds, or if not thousands of papers, and we've spent many, many billions of dollars building increasingly sensitive and accurate devices that would measure, if any, this dark matter's scattering with ordinary matter. And so there is this huge investment that, however, if you dare to put it in perspective in this landscape, looks like this. All right. So the WIMP, or the weak scale dark matter paradigm, is nothing but a very, very thin slice of an otherwise extremely large and potentially viable parameter space for dark matter to live in. Now, across this landscape, there is one particular scale that is special. There's one particular mass that is critical, and that mass owes its name to this cheerful German scientist by the name of Max Planck. And what Planck calculated was essentially the value of the mass at which the Compton wavelength of a particle, a quantity that is inversely proportional to the mass m, equals the Schwarzschild radius corresponding to the same mass. So what does that mean? It means that if you think about the black hole associated with the mass m, its event horizon has a certain size, and the Planck scale is essentially exactly 2 factors of pi, the mass at which the Schwarzschild radius and the Compton wavelength of the particle are the same. What that means is that north, for more massive particles than a Planck scale, you really should not talk about elementary particles, because the quantum nature of these objects is actually entirely overwhelmed by gravity. It's entirely overwhelmed by the classical gravitational behavior of that object as a black hole. Interestingly, as you know very well, there are general theorems in GR that point actually in a similar direction to Wigner's classification theorem, which is that a black hole is generally classified entirely, in addition to its quantum numbers, by its mass and angular momentum. Of course, in classical GR, the angular momentum is not quantized, but sure enough, any theory of quantum gravity better quantize J as well. So today, I will talk about the right half, more or less, of the landscape of dark matter candidates that falls under the general descriptive name of black holes. And I will take you on a journey that will range from the Planck scale to what I said is the maximal scale that we should talk about a point like dark matter constituent, which is in the stellar mass range. Within this black hole mini landscape, so to speak, things have a mass that is macroscopic, that we can actually imagine. I will talk about stellar mass black holes, but then I'll rapidly move on to a very interesting class of black holes that have a mass around an asteroid. So, a fraction of the moon's mass or smaller. There is another very interesting class of masses which roughly equals the mass of a mountain. And finally, we'll talk about much smaller black holes that have the mass of a whale, and finally, black holes that have a mass of a grain of salt. So let's make a few qualifiers before we dig in and we take on this trip in landscape of black holes as dark matter. So I will not talk today about how these black holes, that if they have anything to do with the dark matter cannot be of stellar origin, come from. So this is, a lecture series by itself. And there's many, 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 many ways in which non-stellar black holes can arise. I've been involved in almost all of these avenues. Some of them are very interesting from a field theoretic standpoint, such as the notion that a first order phase transition can trigger, black hole formation in the relatively late universe. Another thing that I've been very passionate about is down here. If you have very strongly self-interacting dark matter, you can seed black holes in the cores of galaxies. But unfortunately, I will not talk about this today. Again, ask me if you're curious. It is important to keep in mind that the mass and the mass distribution of these black holes really is in one-to-one correspondence with the way in which these black holes were born. In other words, the mass function of non-stellar primordial black holes depends entirely on how these black holes were produced in the early universe. So, back in the day, I worked a lot on non-black hole dark matter phenomenology. And the lore back in the day was, roughly speaking, revolving around figures like this. This figure represents, as a function of the mass of a non-stellar black hole in units of the solar mass, which fraction of the dark matter can be made out of black holes if they all have one single mass. So let's say that I pick 10 to the negative 10 right here. I look at the shaded region and I find that, well, maybe 0.5% of the dark matter can have that mass. And another thing I learned from this plot is that maybe at best, a little bit over 10% of the dark matter could be in black holes. Well, this picture is incorrect. This picture is incorrect. And the modern version of this plot, which actually has become a little bit more tightly constraining in certain areas of the parameter space, on the other hand, leaves a large window that I'll talk about today, again, around asteroid masses, where we know for sure today that asteroid mass black holes can be 100% of the dark matter. And that's not a tiny sliver. This is, at least 4 to 5 orders of magnitude that are clearly open for black holes to be 100% of the dark matter. So what went wrong? Well, a few things went wrong. One of them I'll talk about, finite size source effects. Another one I will not talk about, but I'm happy to discuss if people are interested. So now let's embark in this journey that I was outlining, and let's talk about stellar mass black holes. As someone, as Michael remembers, who is very keen on finding a conclusive evidence for dark matter that is not contaminated by astrophysical backgrounds, I really fell in love with black holes upon realizing that it would only take one single detection, and the detection would be of a black hole merger that includes a light black hole below the so-called Tolman-Oppenheimer-Volkoff, or TOV limit, where stars no longer form black holes but form neutron stars, for us to convince ourselves that there exists a population of non-stellar black holes. Now, that's fascinating. It's also technically incorrect, because you could have new physics imposters, such as odd objects that violate the TOV limit. This also involves new physics. And if you're curious about this, we have a recent paper where we study this possibility, and we actually try to understand how to tell black holes apart from non-black hole light sub-TOV objects. But the interesting thing is that if you make an estimate of how many events you may expect out of these let's call them for simplicity, subsolar mass mergers, you actually potentially have a large statistics. With my collaborators, we've determined that the rate of events can be much larger than a few per year in principle. Of course, our friends that look for gravitational waves are keenly aware of this possibility. And the LIGO-Virgo-Cagra collaboration has searched intensely for sub-solar mass black holes. There are no confirmed events that are endorsed by the gravitational wave search collaborations. However, candidates have been claimed by independent groups that have reanalyzed the LIGO-Virgo-Cagra searches. So let me just flash what these events look like in a Bayesian framework. These particular events, which is 170401, actually has, according to this study, a significant posterior probability for one of the two objects to be certainly below the TOV limit, and in fact, below the solar mass limit. Now, if you'll allow me the joke, this is an event that supposedly happened on April 1st. So is it an April Fool's joke? I leave that up to you. What I can tell you for sure is that this is not classified as a gravitational wave event merger at all by the LIGO-Virgo collaboration. Another tantalizing event is 200308, which also involves subsolar mass objects. In fact, in this case, two subsolar mass objects. The nerve-wracking aspect of this detection is that for this type of objects and for the signal-to-noise ratio that was found by this group, the false alarm rate, FAR, is actually one event every 5 years. And so, that's not low at all. This may very well be a false alarm, and that is actually the case if you listen to the LIGO-Virgo-Kagra collaboration. However, to close this quick chapter, I would say that this is incredibly interesting. And please stay tuned because, again, one single detection would demonstrate that at least part of the dark matter is in the form of primordial black holes. So that would be a huge discovery. Of course, it would not tell us how much of the dark matter is in primordial black holes, but it would be the start of a completely new era for astrophysics and fundamental physics. Now, let me get to chapter 2. This is an important chapter because, as I argued, asteroid mass black holes can be 100% of the dark matter. Now, what I will talk about here are two main things. One is that the main technique people have used to search for these objects is really hard. This technique is microlensing. We'll learn everything about it, or a lot about it, in the next few slides. Since microlensing is so hard, the next question is, well, what else? How can we detect these dark matter candidates? This is what a microlensing event looks like. A microlensing event is the transit of a mass in front of a background source. As the mass transits in front of a background source, light gets bent. You may have multiple images, but in the case of microlensing, all you have is an amplification of the brightness of the source that has a finite time duration. So what you need to do to detect a microlensing event is very simple. You just need to look at a lot of stars and one by one look for any one of these stars getting anomalously bright and then back to its original luminosity over some finite amount of time. That's exactly what our friends in Japan did with the Subaru Hyper Supreme camera. They took a long exposure photograph and a series of photographs of the Andromeda galaxy, and they actually could make out with this incredible piece of engineering that is the Hyper Supreme camera, individual stars on the order of millions of individual stars in M31, and they looked for this anomalous amplification. Now, with a team of folks here in Santa Cruz, including experts on the stellar populations of Andromeda, we sought to understand exactly what this observation and the limits that were derived consisted of. And the problem that we immediately found was that the Japanese study actually assumed that all of the stars in their sample had the size of the sun. Unfortunately, the sun is a relatively small star. Here, for comparison, I show a few local stars in the Milky Way. And as it turns out, these larger stars are obviously much brighter and much easier to monitor for the Hyper Supreme camera. In fact, if you look at the abundance of stars, aided by the notion of which stars have which mass within Andromeda, and specialized to this survey, you notice that it's less than 1% of this microlensing survey involves stars as small as the sun. So everything else was much larger. And here is where finite size source effects come into play. So let me give you a theorist picture of what's going on. So again, we're looking at a star with our, telescope right here. We've got a black hole, probably a much smaller black hole than, M87 star, transiting in front of our star. and we see more light. However, if the source is large, that effect is significantly reduced because the lensed light would get to us anyways because of the angular extent of the star. So now, of course, this is a simple picture. If you do things properly in general relativity, you realize that the condition for finite source size effects to matter is that the angular size of the lens be smaller than the angular size of the source. And so if that's true, you significantly reduce the magnification, potentially well below the sensitivity to an enhancement that your observations have. And so to make a long story short, when you take this into account, you drastically reduce the ability to constrain light black holes that have a smaller, in this picture, a smaller lens Einstein ring size. And so the bottom line is that you have a very, very large window, unconstrained by microlensing, unconstrained by any other type of constraint, where black holes can be 100% of the dark matter. Now, interestingly, this microlensing actually has been detected many times, hundreds of times, most recently by a survey dedicated to search for objects like primordial black holes, OGLE, and many other relatively similar surveys. And as you see, the shape of this magnitude amplification follows beautifully the one that encompasses the finite size source effects. Sadly, black holes are not the only thing that can produce these events. If you have a dim star or a planet in the range of masses that are of interest to us, then you get exactly the same gravitational lensing effect. So what are these planets? Well, these planets cannot be bound to stars, otherwise you would see the star. They are freely floating planets, also known by the much catchier name of rogue planets. These rogue planets arise in a number of possible ways. The most common one is simple three-body ejection. You have a planetary system. Because of three-body interactions, like planets tend to get kicked out. The good news is that there is, if our crazy president lets it be, there is a telescope that is slated to go in orbit in a couple of years, the Nancy Grace Roman Space Telescope, that will be entirely devoted to studies of microlensing and more broadly to the galactic bulge. So that's great. But on the other hand, it's important to realize that freely floating planets or rogue planets are an irreducible background to searches for primordial black holes. So the question is, will this new powerful tool that will come online in a couple of years enable us to disentangle freely floating planets versus them, the background, plus black holes? So this is what we studied with my collaborators. And actually, one of my collaborators, Will DeRocco, who's now a postdoc at Johns Hopkins, has, in the meantime, become the leader of the Roman science group on rogue planets. So what we did was to just study the statistics of the event duration. So in other words, what we did was to produce synthetic catalogs and simulations of PBH and rogue planets with different assumptions on the PBH abundance. Please note that these abundances are very small. They're very, very small. And we tested with simple statistics whether or not you could discriminate a population that follows what is theoretically predicted for rogue planets or that follows primordial black hole mass distribution and the velocity distribution. And in some cases, you're lucky. Like in this case, you clearly see that there is an excess. In some cases, you're not so lucky. In this case, you cannot discriminate the two populations based on duration by itself. Of course, there's other follow-ups, location in the sky, velocity distributions, follow-up observations that can disentangle, but at a minimum, we'll be able to do this exercise. And in fact, we anticipate the sensitivity of Roman to be exceptionally good. Please notice that the abundance of rogue planets is actually predicted to be incredibly large. So for every unbound Earth mass planet, uh, there is at least one bound planet. But predictions are that there's actually many more than one unbound per bound planets. So for every bound Earth, there may be up to 100 unbound Earths floating around in this cold galaxy with no hope of life on them, just, free streaming in the galaxy with nothing better to do than being a background to my black hole searches. So Roman will be great. And more interestingly, we will know for sure whether current surveys are observing black holes or free floating planets. So stay tuned. But this begs the problem, how can we otherwise access the asteroid window? Let me just throw out there a few things that people have come up with. One is if you produce asteroid mass black holes in the early universe, as many, including in this audience, have worked on, then you generally could predict a spectrum of isocurvature perturbations that produce gravitational waves. However, this is model dependent. This does not necessarily happen in all production mechanisms. You could think about looking for smaller objects with higher frequency light, but unfortunately that's not practical because sources at very high frequency are very scarce in the sky, and usually telescopes have not reached the angular resolution of, say, the Hyper Supreme camera. There's other ideas. We've worked on LIGO-style black hole mergers. So what happens in this case is you have exactly the same thing that happens with LIGO, two black holes merging together, producing a larger black hole and gravitational waves. The inspire is exactly the same, but it's scaled up in frequency by as much as the mass is scaled down. So here we're talking about 1,000,000,000 times smaller than solar mass, meaning that the frequency of these mergers is gigahertz instead of hertz. So how can we detect them? We don't really have gigahertz gravitational wave detectors, but we can recycle things like ADMX. And of course, you all know about axion searches with resonant cavities. So the idea is that gravitons actually couple to electromagnetism, and this is the so-called Gerstenstein effect. And so, a vertex graviton photon exists in just the same way that an axion photon vertex exists. And so you can think of exactly using the same technique that you employ to search for axions to search for high frequency gravitational waves. And believe it or not, I don't know why, but people in ADMX have trusted me to join forces and look for gravitational waves with ADMX. So I'm really excited, and we have results soon. There's another possibility that my current and former postdocs have worked on, which is if these asteroid black holes are the dark matter, they may kick gravitationally planets around. And that's also an interesting possibility that may lead to detection. But, I would say that the phase space for discovery techniques in the asteroid window is not exhausted at all by this list. And so we really need good ideas, and we really need good people that think about how to go after these objects. Black holes explode. We've known this for a long time. We've known that if you put a quantum field theory on the background of a Schwarzschild geometry, then for an asymptotic observer, a black hole has a temperature. And the temperature is given by this combination of the Planck mass and the black hole mass. So given that an object with a temperature radiates, and it radiates like a black body, we can understand how black holes emit light and any other particle, just like any other black body, in very simple terms. In fact, everything we need is the Stefan-Boltzmann law that we all learned in our scientific youth, says that the luminosity of a black body is proportional to its area times the fourth power of its temperature. Now, the area of a black hole scales with the radius squared. The radius is, as we saw before, proportional to mass. But the temperature is 1 over the black hole mass, right? So you have mass squared from the area, 1 over mass to the fourth from t to the fourth. So dm dt, the change with time of the mass of a black hole, goes like 1 over m squared. So this is interesting because it produces a runaway process in the context of this that, of course, is known as black hole Hawking evaporation, that Hawking himself called black hole explosion. Now, if you integrate this differential equation, you find immediately that the lifetime of a black hole goes with the third power of mass, and therefore, black holes have a finite lifetime. And in fact, if a black hole weighs 5 times 10 to the 14 grams, it has a temperature of about 100 MeV, and it's exploding right now. It's exploding today because its lifetime equals the current age of the universe. If it's a little bit more massive, it is slowly evaporating. It's not gone yet. So the beauty of black holes is that the way in which they evaporate is absolutely universal. In other words, any black hole has a light curve, an emission of particles, say photons, as a function of time that is absolutely identical to that of any other black hole. So these are really perfect standard candles. Today we had here at Santa Cruz a colloquium by Josh Freeman, who talked about, of course, supernovae as standard candles. Supernovae are really crappy standard candles when it comes to comparing them to black holes. These really are absolutely universal. Also, the way in which the process works, which is a sudden increase in luminosity followed by nothing, really hints at a structure that is reminiscent of gamma ray bursts, but backwards. So instead of having an afterglow, you kind of have a pre-glow. You build up and then the object completely disappears. Notice that people have thought about the possible afterglow of black hole evaporation, but I can tell you, and I can go into technicalities here, that black holes actually have no afterglow at all. They don't have a photosphere or a chromosphere. Please notice that I have two curves on this plot. One is for the standard model, another one is for this now not so popular theory that myself and many of you guys in the audience used to love, supersymmetry. If you have supersymmetry, you suddenly, as soon as you go through a temperature equal to the SUSY mass scale, you produce SUSY partners. And so all of a sudden you evaporate twice faster. And so I cheated when I said that they're perfect standard candles. They're perfect standard candles if you know the particle counter standard model. If you don't, well, black holes are a great portal onto any dark sector if you measure this light curve. So can we measure this light curve? Well, there are two things that we should keep in mind. One is, what is the mass of the black hole that is evaporating? Because that depends, that fixes the temperature. It fixes how hot the black hole is. And on the other hand, we have distance, right? As anything else in astronomy, it will be easier to see an exploding black hole closer to us than farther away. Notice that here the distance is under parsecs. So we're talking about really close by stuff. So let me remind you, and this here, the horizontal axis is mass in grams, that there is a relationship between the lifetime and the mass that looks like this. And so black holes in the asteroid mass range are up here. They don't really evaporate. But as soon as you go below that threshold of 10 to the 14 grams, black holes start evaporating quickly. At 10 to the 12, it takes them about 12 years. At 10 to the 11, it's already just 5 days. And for a ton black hole, so for a black hole of 10 to the 9 grams, it just takes a fraction of a second. to evaporate. In turn, when you think about temperature, these objects get hotter as they're lighter, and they are, in this case, inversely proportional in relation to mass. They get colder as they get heavier. So how are our telescopes good at detecting these explosions? Well, it depends, right? It depends on your telescope. For instance, very high energy telescopes like CTA Veritas, the Chinese version of Hawk, which is called LASSO, do very well. And they are mostly the most sensitive things you have. The Large Area Telescope, the LAT, the Fermi telescope, does also very well. And so do gamma ray burst telescopes as soon as black holes are cold enough that these high energy telescopes don't detect anything. So in this plot, of course, anything that is below the lines is detectable. Now, the shape of these contours of sensitivity shouldn't come as a surprise. Here, the bursts are very, very short. So, you just need enough time to collect enough photons. Here, the limiter is just the observation time. Telescopes usually have a lifetime shorter than years. And finally, here, the problem is that the black hole temperature gets so low that photons are not energetic enough to be visible. So the one thing that I'd like to draw your attention now to is that these distances are very small. The distance between the Earth and the Sun is right here. So we're talking just, a little bit above the heliosphere and the very, very local universe, parsecs or tens of parsecs. So if there is a black hole explosion that lasts a decent amount of time, you should see this exploding black hole move in the sky. You should see the explosion have a proper motion, which can be large. Okay, so this dotted line is a proper motion of 0.1 degrees if the black hole is moving, transverse to your direction, 1 degree and 10 degrees. Good. So this being said, what we did was to look at variable sources and to look at the spectrum of these variable sources, which also is universal for evaporating black holes. And we found a bunch of candidates of sources that look like they're evaporating in exactly the same way that we would expect a black hole at this distance and with this mass. So yay, we've detected Hawking evaporation. We found evaporating black holes. Or maybe not. Again, this is 1 AU. These things would be incredibly close to us, roughly between us and Jupiter. So they should have a large proper motion. But unfortunately, none of these sources has any proper motion at all. And that's extremely unlikely. Even if the source was exactly aligned along our line of sight, we would see it getting dimmer, or we would see some deviation, but nothing is detected. And so unfortunately, these are candidate events, which means the searches can be done, but without proper motion, there is no conclusive evidence that this can be associated with evaporating black holes. We did the same thing, and we are continuing to do this with short duration gamma ray bursts. Actually, this is a little more promising, I think, because there's actually a network of gamma ray burst detectors in the sky that can be used to triangulate the arrival direction of photons. And in this way, through triangulation, you can actually find if an explosion is nearby or if it's at cosmological distances, as GRBs should be. And so we are connecting GRB detections with multiple spacecrafts and their timing information to look for exploding black holes. Good. So evaporation relics, of course, can be directly detected, but could also be sort of indirectly detected. And so one possibility is that we detect the remnants as diffuse gamma ray emission or cosmic ray particles of black hole evaporation. Now here, for the particle physicists in the audience that like UCD, and I know there's many of you, the issue is that for temperatures of interest to capturing evaporating black holes, we are at temperatures close to the QCD confinement phase transition. And this means that doing particle physics there ain't easy. But, answering the question, how do black holes with a temperature close to the QCD phase transition evaporate, is a well-posed question that you can tackle with the arsenal of tools that we know of to deal with, essentially light hadrons and mesons and light hadrons. And as a bonus, what we did was we created a code that is called HASMA that allows to calculate correctly and to just give you a visual, very, very quick visual of how out of the blue the previous predictions were. The correct version is this that can be calculated with our code. Previous estimates were this dashed line and this other dashed line. So it's not small mistakes. Doing hadron physics properly for black hole evaporation around a QCD temperature, very, very important. And of course, you can set limits. I don't have time to go through this, but again, there's been some issues in the literature, so please be careful. Now, what happens if black holes are light enough that they're gone? They have exploded in the early universe and they're gone. Well, lots can happen. So one of the things that myself and my graduate students have worked on is you can actually use Hawking evaporation as a source of dark matter and as a source even of the baryonic symmetry. There's several ways to do so. One way that is, I think, rather clever is to directly do baryogenesis at the event horizon by postulating some effective operator that couples the B minus side current to a relativistic invariant that is not a constant, it's not a conserved quantity in an evolving evaporating black hole. For instance, the Kretschmann scalar. There's many other possibilities, but we showed that this particular realization works to produce the baryonic symmetry in the universe. And you can also use gravitational waves to search for black holes that have completely evaporated in the universe, but you want to detect them today. So again, ask me if you're curious. Now, we've arrived to the last chapter of our journey, which is grain of salt black holes. Now, the Planck mass is really weird. The Planck mass is the mass at which quantum gravity comes into play. It's the mass that corresponds to a distance where we think space-time no longer looks like the space-time that we know and love, where quantum foam is supposedly arising and many other interesting things. But the Planck mass is also a macroscopic quantity that in fact equals roughly the mass of a grain of salt. So here I'm talking about Planck relics. Now, Planck relics need not exist. We don't know what happens to physics in general, let alone quantum field theory, let alone Hawking evaporation when we approach the Planck scale. You have to have a full theory of quantum gravity to really get close to the Planck scale and answer the question, does evaporation stop or not? However, there are several arguments within quantum gravity that point to the possibility that evaporation stops at the Planck scale. In fact, some of these arguments entail that the relic that is left over has an electric charge. So how is this possible? Well, one possibility is that even if evaporation does not stop at the Planck scale, you may stochastically charge a black hole near the Planck scale in a way such that its Reissner-Nostrom horizon, which is different from the Schwarzschild horizon, shrinks to zero. Evaporation then stops. The black hole is extremal because of electric charge, of course, also or magnetic charge or any dark charge. And you have a relic, right, that is a little bit more massive than the Planck scale or a little bit below the Planck scale. Now, there are processes that may discharge this black hole. And in fact, I have recently studied how black holes discharge around the Planck scale and for much more massive scales. And my conclusions are pretty pessimistic. So you may want to check out this recent paper of mine. But in the paper itself, I point out that it is possible for these relics to exist with a charge today, okay, to not get discharged and to preserve their charge today. If that's the case, then this is very exciting because you can actually use techniques inherited from searches for WIMPs and massive dark matter candidates, such as paleodetectors or neutrino detectors, that are essentially small chunks of material that, because it found itself deep, deep underground, it did not get contaminated by cosmic rays, and a defect that would be imprinted by the passage of a charged massive particle would be clearly detectable upon inspection. Well, these paleodetectors would allow you to discern even a fraction of 1 part in 10 to the 4 of charged Planck relics if these are in fact the dark matter. So that's pretty exciting. So let me wrap up here. I've taken you into a journey that started with stellar mass black holes. I'm really excited because I think we will soon see a sub-solar or sub-TOV event that will point towards exotic black hole physics. Searches are ongoing, so please stay tuned. Asteroid mass black hole, we now know with certainty they can be 100% of the dark matter. Microlensing is a lot trickier than we thought for different reasons. And we really need a new and creative way to think about how to detect these objects. The main background are these rogue planets. So we got to come up with something that fights this background and that will deliver a conclusive evidence if these are in fact the dark matter. Black holes evaporate, so we can look for these explosions. These explosions are fascinating because they also are windows on dark sectors. So if dark sectors exist, black holes evaporate more rapidly, and we can directly see this effect if we were to detect an exploding black hole. If black holes are gone by now, so they're light enough to have completely evaporated, they can still have to do with the dark matter, especially with dark matter production, but maybe also the production of baryonic symmetry or gravitational waves that would travel undisturbed all the way to us today and could be detected, for instance, with resonant cavities like ADMX. And finally, black holes may be really tiny. They may weigh as much as a grain of salt. If they're charged, then they are detectable, and this is best done with paleodetectors. So I'll leave you with this slide, and I'd be very happy to take questions. And I thank you very much for your patience, for hosting me today. And again, apologies for not being there in person. I promise that upon the next invitation, you will have me in person in Seoul. So thank you again.
Thanks for the nice talk. Yeah, so are there any questions?
I have a question. Can I ask?
Of course, Sarif, please go ahead.
So I have a because I don't talk on black hole, but I have questions. So all these particles basically comes out outside of the event horizon, not in from the inside of the, because anything cannot come out from the inside of the event horizon, right?
That's right. That's right.
Okay.
Yeah. So you know, there's this famous picture of a pair of particles that are produced right next to the event horizon, and one of them you know, falls inside the event horizon and is captured by the black hole, but one may escape. And if that particle escapes, you know, this may give you an idea of how Hawking evaporation happens. So it's, you know, it's a semi-classical process that happens right next to the event horizon. This actually is not a technically correct picture. The technically correct picture is one where you have a free-falling observer,
Yeah.
and you essentially translate the annihilation and creation operators in quantum field theory to a freely falling operator, to a freely falling observer. And immediately you realize that you have this effective temperature, and so that for an asymptotic observer, a black hole sheds particles just like a black body with a well-defined temperature.
Okay. And one more question, in the case of the the black hole evaporation, so if we consider it as a dark matter, and as you know that dark matter should be non-baryonic, so it should not decay to standard model particles if it is a dark matter.
I guess another way to rephrase your question is, wait a second, there are conservation laws that prohibit, say, producing a single electron. So now gravity doesn't care, right? Gravity doesn't care about conservation laws, and so it's totally fine from that standpoint. Gravity doesn't care at all about classical gravity doesn't care at all about quantum mechanics. And so, if any particle exists, gravity only sees that a particle has or not a mass, and it spits it out in the same way that a black body spits out any particle, right? If you were to crank up your oven temperature to a temperature of 100 TeV, you would produce a standard model in your kitchen.
Thank you, Professor.
Kiyoharu-san, please.
Okay, thank you for nice talk. I really enjoyed your talk.
Thank
But
you.
I have a question about the last part, about the Planck mass remnant.
Yes.
So, do you consider extremal black hole remnants in your talk?
Yes, so that's a possibility. So one way to shut off evaporation is for the black hole to have zero temperature, right? Because a zero temperature black hole does not emit any radiation. In the case of Schwarzschild, that means that the black hole mass is infinite, right? But for spinning black holes or for charged black holes, you can get a zero temperature by virtue of the fact that the black hole is rotating or carries a charge. And so one way in which you can stabilize against evaporation a black hole and charge it is if you have an extremal black hole. So that's one possibility. Another possibility is that Hawking evaporation as a quantum field theory mechanism just shuts down because of quantum gravitational effects. That's a distinct possibility. So it's either one, right? Either one would work. And the problem with electric charge is that you can also discharge it by Schwinger pairs. And here the idea is that, very close to the event horizon, you have incredibly large electric fields, because Coulomb forces go like 1/r squared, and R is very small. And so if you have a very large electric field, you do per production, right? And so that's the Schwinger pair discharge. Again, it's independent of Hawking evaporation. It's just a notion that near the event horizon, you can pair produce, imagine any plus, E minus, and then if your black hole is positively charged, you eat the E minus and you spit out the E plus, and you've discharged a black hole. So again, Schwinger pair discharge is is a quantum field theory effect that may shut off near the Planck scale. But actually, string theory says that it should not. So string theory and certain incarnations of quantum gravity actually predict the Schwinger discharge should not be shut off at the Planck scale. But we don't know, because we don't have a quantum theory of gravity. So,
Yeah, I just wanted to know. So, yeah, how you get Planck mass remnant in your setup, or
yeah.
yeah.
I don't care how. So there's different possibilities, right? So it's either evaporation stops because Hawking evaporation is semi-classical, so no longer valid, or extremality.
Okay. And then, so I see. So
And then you're stuck, you're stuck with a Planck relic. You don't know whether or not it's charged because you can become extremal, for instance, with a magnetic charge or with a dark charge. So it doesn't have to be electrically charged. But if it's extremal because of the electric charge, then for sure it will carry a charge.
Okay, so forget about how we form such a remnant. So your point is so you can detect such remnants.
Exactly.
Okay. Thank you.
And in fact, this is very liberating because if you produce light black holes, they will evaporate very quickly. And so it doesn't matter which mass you produce them. If they're light enough, below 10 to the 14, very plausible in inflationary production, then you're stuck with Planck relics if they're stable.
Okay, thank you.
Well, did you get bound states of these relics?
Excellent question. Yes, you can get bound states. But Philip, if you can imagine, back in the day when we learned the hydrogen atom, in fact, we learned it in a way that assumed that the proton was infinitely massive, right? So these would actually be essentially, very heavy atoms with exactly the same structure as the ideal hydrogen atom, where the proton is just an infinitely massive point object. Now, the problem is that,
The electron is also massive.
well, no, the real problem is that it's very easy to reionize the universe. In fact, we know that there's essentially no bound hydrogen around in abundance. And so all of these things would have been ionized very early on.
Well,
So,
I mean, but that comes from like X-rays and so on, right? That reionizes the universe. But I imagine that if you had a bound state of two uh, mass relics,
two black holes.
yeah, two black
Good.
holes. Yes.
Very good, very good. That's a very good question. So if you have bound states of two charged black holes, then yeah, that's a very interesting question. Then what would happen? Well, you obviously would not have the same tracks in paleodetectors, right? Because you would have a bound object. You would have some screening of the charge. Right. I think you're fine with stability, Philip. So that's an interesting question. Send me
Yeah,
an
I mean,
email. Well, actually, I have your email. So let's
sure, yeah, I'll
think
send you an
about
email
this.
after. Yeah, great.
Very, very good question.
Uh, Thank you very much for this talk. And you did not talk much about the production mechanism for PBH. So, uh, and you mentioned that depending on the mass scale and the mechanism, the mass function varies. Are they? I was wondering whether those mass functions are calculable or predicted in a reliable way or not. Could you make some general comment on that? And also,
Yeah.
the second question is, I noticed that there were some recent works about the memory burden effect. And could you comment on those the
Yes.
memory burden effect? Yes.
Yes. Thank you, Pyongwan. Two very, very good questions. So each one of these mechanisms would produce a different mass function. So what are the, for instance, mass functions you would expect from, let's say, the notion that in the early universe, you can have a relatively small overdensity, in fact, of order 20 to 30%, and collapse critical collapse into black holes. Well, in that case, there are general predictions that the mass function will be essentially log normal. And so, there's a very easy, straightforward way to map the width of the mass function with, for instance, the inflationary potential and the scale of the density perturbations that it produces. And so, that's very straightforward. The mass usually, Pyongyang, is simply related to the so-called Hubble mass. So if you produce an object at a given redshift, the object will have a mass equal to, whatever mass corresponds to one Hubble length at that epoch. So, for instance, self-similar production mechanisms like cosmic string loops, they tend to produce truncated power laws with predictable slopes. For instance, this mechanism that we studied with my students, you posit that there is a dark sector that forms dark stars, and you collapse these dark stars. And so you imagine that the mass function is similar to astrophysical black holes, just shifted depending on the mass of the dark proton. So it really depends, but generally the literature is pretty advanced in in telling you what happens to the mass function for a given production mechanism. Essentially, the trick, Pyongyang, is to look at the temporal development of the production of black holes and weighing each moment with the Hubble mass corresponding to it. So you sort of have this integral over Hubble masses as the production mechanism proceeds in the early universe. Now, for the memory burden effect, it's funny you should ask, because we actually looked into that specifically for black hole evaporation. Black hole evaporation is completely different if there's memory burden effects. And of course, what that means is that the mass of black holes that may be evaporating today can be much, much smaller. And so everything I've said about, black holes having exploded in the early universe changes dramatically. But what we worked on specifically was the shape. You remember I talked about standard candles, right? So that also depends on considerations also around memory burden effects. So if those are there, that light curve changes and in fact gets scratched very significantly. So that's interesting, because you can have a light black hole, which means a lot more abundant, right? Because if you want it to be the dark matter, there's got to be a lot of them around, that is currently evaporating, because the evaporation is very slow, so they're not evaporated away. And so, if memory burden effects are real, if we can convince ourselves that that's not just purely speculative, then then black hole explosion detection would be much easier than in the standard model.
Good. Oh, thank you very much for your wonderful talk. And I have to digest your slides.
Certainly, Pyongyang, I'll send
And
them
then
to you.
I will ask you further questions by emails. And
I will be delighted. Thank you again, you all. And as I said many times, I hope to see you in person soon.
okay, yeah.